All right, so today we're going to delve into amines more deeply. We're going to start out with nomenclature. Then we're going to talk about physical properties, spectroscopy, interesting amines. There's a whole bunch of amines in that category. Then we're going to conclude by discussing ways of synthesizing amines, including some methods that we've already learned previously in class and some new methods that can be used. So starting out with nomenclature, if we have a primary amine, naming it is very simple. We just take the chain that is attached to the nitrogen, drop E from the parent name, and add amine. So we get ethanamine. If it's a ring, we have cyclohexanamine. In parentheses, I have a common name system, which is equally as common as the IUPAC system, and that is naming those groups as alkyl groups. So they would end in "-il" instead of ending in "-n". So ethylamine, equally valid as ethanamine for this compound. Cyclohexylamine, also equally valid as cyclohexanamine. So I'm sorry there's two different systems, but they're close enough that hopefully you can recognize both of them and not get too confused. Now, if we have secondary or tertiary amines, the simpler kinds of secondary and tertiary amines are the ones where the 2 or 3 alkyl groups are identical to each other. And in those cases, we use our common name system where we name the alkyl group, but we just use di or tri as our prefixes. So ones that we've seen before. What's the name of this compound? Okay, that's the conjugate acid of LDA. That's where we've seen it. We called it lithium diisopropyl amide when it was LDA. What would we call it as the amine? We would just call it di because there's 2 alkyl groups. Isopropyl, that's what our alkyl groups are. Amine, okay? Very straightforward. And a tertiary amine, a relatively common tertiary amine is this one right here. What would we name this compound? Triethylamine, yes. And that's one of our most common amine bases that are used when we need a weak base in an organic reaction. Most people who've worked in organic labs have used triethylamine at some point in the lab. If we have different alkyl groups in a secondary or tertiary amine, then this figure here is going to show us how to name those compounds. What we do is we take the longest chain or the largest ring and we use that as the parent, and we can assign it a name either using the common or the systematic system. It wouldn't matter. So this would be either isopropylamine or 2-propanamine. And then the other group or groups are named as substituents of that name. And you put an N in front of that to indicate that those substituents are attached to the nitrogen. We're used to seeing numbers used for substituents, but that nitrogen doesn't have a number in the molecule. And so we put an N to indicate that in this molecule, the methyl group is attached to the nitrogen. Okay? Any questions on naming our more complicated secondary and tertiary amines? Okay, we can also have aromatic rings bonded to a nitrogen of an amine. And those compounds are named as derivatives of aniline. Aniline is, remember, from chapter 17, when we have NH2 attached to a benzene ring. So if we have more complicated aryl amines, we just name them as derivatives of aniline. Okay? So there's 2 ways to do this. If it differs from aniline by having another group on the nitrogen, we just use the same N system that we showed you here on the screen. We would just call this N-ethyl aniline. Or we could have molecules that differ from aniline due to having other substituents on the benzene ring. So what would we call this compound? Think back to our aromatic nomenclature. Okay, we could call it 2-bromo. We'd probably use a letter instead. What letter would we use? Yeah, it'd be O for ortho. Orthobromoaniline. Okay, so that's how we would name aromatic amines. A couple of other issues related to amine nomenclature. Sometimes we need to name an amine as a substituent. If we have a molecule that has an alcohol, for example, that alcohol gets priority, and so the main name of the molecule is based on the alcohol. And if the amine is coming off another carbon somewhere in the molecule, we would need to name it as a substituent. So when we have an amine as a substituent, it's referred to as an amino group. Okay? So whenever we need to name an amine as a substituent, we just call it amino. And then we have some heterocycles, some rings that contain nitrogen that have common names. Some of these you've already seen before. The first one here, everybody should know the name of this molecule. What do we call this? That's pyridine. Here's another one that we learned about back in chapter 17. What do we call this compound? That's pyrrole. Okay. So these are the saturated nitrogen heterocycles, and they're also aromatic. And then we have unsaturated versions that have common names. Okay. So a 6-membered cyclic amine is referred to as piperidine. And then a 5-membered cyclic amine is referred to as pyrrolidine. So these are common names for amines that we need to be familiar with. Okay? Any questions on nomenclature? Let's talk about spectroscopy now. So what interesting feature of amines in mass spectrometry did we learn about last semester? Trent? Okay. So when you have an odd molecular weight, that indicates that you have an odd number of nitrogen atoms. Since we're typically dealing with relatively small molecules in this class, the vast majority of the time that we encounter an odd molecular weight, we would have 1 nitrogen atom in that molecule. Okay? So that is an important feature of the mass spec that we need to be aware of when we're trying to solve problems where we're trying to determine the structures of compounds based on their spectroscopic data. In the IR spectra of amines, we'll come back to that in a moment. In the IR spectra of amines, we have the the NH stretch that appears usually between 3200 and 3500, kind of in the same range where OH stretches appear. Of course, if we have a tertiary amine, there will not be an NH stretch. So if you have a molecule that has a nitrogen atom according to the mass spec and no NH stretch, it might be a tertiary amine. If it is a secondary amine, it has 1 NH peak because there's only 1 NH bond. If it's a primary amine, it has 2 peaks in that region. And that's because the stretching of those 2 NH bonds are coupled to each other. They can stretch in a symmetric fashion, meaning they're stretching and contracting at the same time. Or they could stretch in an asymmetric fashion where they're off, 1 bond is stretching and 1 bond is contracting. And so those 2 stretches will appear at different positions in the spectrum. Okay? Questions about IR? Yes? There is, but it's going to be jumbled in the same region as carbon-carbon, carbon-oxygen sigma bonds. They don't differ from each other enough to be diagnostic. And there's so many of those sigma bonds in a molecule that it just ends up being a forest of peaks. That's in that region that's known as the fingerprint that we usually don't interpret because there's too many peaks there. So it's only the the OH and NH region, CH, NH, and OH region where we can have diagnostic signals. Okay. Let's take a look at NMR of amines. And a couple things we notice here. Our NH peak can show up in a wide range. It can show up anywhere from 0.5 ppm to 5. Why do we have such a wide range of possible chemical shifts for an NH? I'll give you a hint. It's the same situation with OHs. Alcohols are the same. They appear across a wide range. What do OHs and NHs have in common with each other? What can they do with each other? Many? Yes, they can hydrogen bond to each other. And so whenever you have a proton that can be involved in hydrogen bonding, it's going to appear in a wide range of chemical shifts because the extent of hydrogen bonding will depend on the concentration. If you have a very concentrated solution of your sample in your deuterated chloroform or other deuterated solvent, you're going to have a lot of hydrogen bonding because of that high concentration. If you have a very dilute solution, you're going to have less hydrogen bonding. And so the extent of the hydrogen bonding will cause that signal to move around. So even if you have 2 or 3 different samples of your N-methylaniline, you're going to see that NH at a different spot in each case. But since the other signals don't move, then you can assign the position of this usually by process of elimination. Okay. The other feature we see is there's no splitting, and that's the same with OHs. NHs and OHs are not split by their neighbors, and they do not split their neighbors. So this is a singlet. The methyl group on the nitrogen is also a singlet. Why is that? Why is there no splitting with NHs or OHs? This was one of those topics we covered probably after Thanksgiving, so we covered it on the videos. When you have a proton on a nitrogen or an oxygen, that proton can rapidly exchange from one molecule to another by acid-base chemistry. Okay? So this nitrogen gets deprotonated by another molecule of this amine, and it gets protonated by another one. So if you were to track an individual proton, it's going to move rapidly from one molecule to another. So rapidly and fast that it cannot detect the spin states of the neighboring hydrogens. If you remember, the splitting patterns are caused by the different spin states of the neighboring hydrogens. Protons on oxygen and nitrogen are not on a single molecule long enough to detect those different spin states, and as a result, there's no splitting. So we see a singlet for the NH, a singlet for the N-methyl group. And then finally, we see that this N-methyl group appears between, or it wouldn't have to be a methyl group, but when you have hydrogens on a carbon that is bonded to a nitrogen, those hydrogens will show up between about 2.3 and 3 ppm. Okay? So we have a de-shielding effect of this nitrogen. If we were to compare that to hydrogens on a carbon attached to an oxygen, would these signals be upfield or downfield of the hydrogens on a carbon attached to an oxygen? Think about how we determine chemical shift. Yes. Yes. The hydrogens, so if we replace this nitrogen with an oxygen, this methyl group would shift downfield to a higher chemical shift. It would be above 3. And that's because the oxygen is more electronegative and therefore more de-shielding. So nitrogen does de-shield these hydrogens. If we had a methyl group with no nitrogen, it would be way down at 0.9. But it does not de-shield the hydrogens as much as an oxygen would. If we had an oxygen, it would be probably about 3.6 or something like that. Okay? Any questions about the spectroscopy of amines? Yes? That's a good question. I don't think it impacts it too much. Not enough for us to make distinctions in this class, certainly. So, all right. Let's go back to physical properties of amines. And there are a couple of features here that are important. First question I'll ask you, can amines hydrogen bond to each other? Can they hydrogen bond to each other? Okay, I see some nodding heads. I see yes. I heard some other things, which might have either been it depends or no. So all those answers are correct. It depends is the best answer, because primary and secondary amines can hydrogen bond to each other, whereas tertiary amines cannot. There is no NH with tertiary amines. So a couple consequences of this. One we see right here. Tertiary amines have significantly lower boiling points than secondary or primary amines of similar size and shape. Here we have two constitutional isomers. Tertiary amine has a much lower boiling point than the secondary amine due to no hydrogen bonding here. So when we compare the hydrogen bond between amines, two molecules of an amine, to two molecules of an alcohol, would those hydrogen bonds be equivalent, or is one going to be stronger than the other? And if one is, yes. Exactly. So I was going to say, if so, why? And the reason you explained very nicely, oxygen being more electronegative than nitrogen makes the OH bond more polar than the NH bond. The more polar bond has higher partial charges on each atom, and therefore the hydrogen bonds are stronger. So hydrogen bonds between amines are weaker than hydrogen bonds between alcohols. And we can see the impact of that when we look at this boiling point comparison here at the top of the slide, where we have an alcohol and an amine, same shape, same size, only a 1 unit difference in molecular weight because of the difference between nitrogen and oxygen. And we see a significant difference here in boiling point, right? 40-degree difference in boiling point between these two compounds, solely attributable to the stronger hydrogen bonds between alcohols when compared to amines, requiring more energy to break apart those hydrogen bonds to convert the alcohol from the liquid phase to the gas phase. So our hydrogen bonds between amines are weaker, but they're still hydrogen bonds, which means that amines will have significantly higher boiling points than other molecules that cannot hydrogen bond to each other, such as ethers. We have an ether here, again, essentially the same size and shape. Its boiling point is 40 degrees lower than that of the amine. So the amine is positioned in between polar molecules that cannot hydrogen bond and alcohols in terms of its boiling points. Any questions? Will amines be soluble in water? Yes, all types of amines or just primary and secondary? The answer is all types of amines, because a tertiary amine is able to hydrogen bond to water molecules. It cannot hydrogen bond to itself, but a tertiary amine can hydrogen bond to water molecules. So you see down here all amines having less than or equal to 5 carbons per functional group that can hydrogen bond to water will be water soluble. Any questions on our physical properties? Okay, let's talk about interesting amines. And we could spend all day talking about this, even the rest of the semester, because there are lots of amines in nature, in the pharmaceutical industry, that do lots of different things. But the first amines we will talk about are smelly amines. Amines generally stink. We've learned that carboxylic acids stink, but amines stink in a different way from carboxylic acids. Carboxylic acids smell like vomit and sweat, moldy cheese, all those sorts of things, whereas amines smell like fish. And literally, they do smell like rot fish because the odor of rotting fish comes from an amine. When fish or any other sort of animal dies and the flesh rots, the proteins in that flesh get degraded and trimethylamine is produced. And trimethylamine has that odor that is responsible for the rotting fish smell. So any fish will have kind of a hint of that. The older the fish is, the stronger that odor is going to be. And then these compounds, as the name suggests, due to the stink of them, due to the fact that they can be found from dead bodies, these are very descriptive names. The names of these are due to the bodily fluids that they can be isolated from. So all of these things indicate that amines do have this kind of fishy odor. Okay, so you've smelled them in many different settings, I'm sure. So what do many people put on their fish when they're eating fish in order to make it taste better? There's a couple different, lots of different choices. You could put tartar sauce. You could put soy sauce or other sorts of things. You can also put lemons or limes. Many times when you get fish in a restaurant, you get a little piece of a lime or a lemon, and then you squirt that lemon or lime on the fish. Not only does that improve the taste, it also improves the smell. And of course, our senses of taste and smell are intertwined with each other. Anyone who's lost their sense of smell due to COVID can probably tell you that. So we're actually doing acid-base chemistry when we put lemon juice or lime juice on fish. We have citric acid in lemons or limes. And we learned back in chapter 22, but many of you didn't learn it until you missed it on the exam, that when you mix an amine with a carboxylic acid, we have an acid-base reaction. Right? We don't make an amide, we have an acid-base reaction. And so what happens is the citric acid in the lemon or lime juice protonates the trimethylamine. This has a very low boiling point, low molecular weight, tertiary amine, no hydrogen bonding. That's why it stinks so bad, because it's volatile and it vaporizes very easily, and we can detect it. Now, if we protonate that nitrogen, we now make a salt. That salt is not volatile. It has a very, very, very high boiling point, and so we're not going to smell it. So that's why we put lemon juice or lime juice on our fish, to perform this acid-base reaction that's going to neutralize that odor. Okay, any questions? So now next time you eat fish, you'll know what's going on, and you can inform your friends you're eating with about your chemical knowledge. All right, other interesting amines are known as alkaloids. Alkaloids, the term alkaloid comes from amines from plants. Okay, here's the word, alkaloids. But it's evolved to mean amines that are derived from plants. And even some amines that aren't derived from plants are called alkaloids these days. But classically, that's what it meant. There are lots of amines produced by plants for lots of different reasons. And we have some here on the screen. We've talked about some alkaloids previously in class. Morphine is an alkaloid. Heroin is derived from morphine. Even though heroin is not a naturally occurring compound, we'd still call it an alkaloid because it's readily available from a naturally occurring compound. We talked about ergot alkaloids coming from the ergot fungus, and LSD is a relative of those, that family of alkaloids. And here we have some other ones here. And many of you have probably heard people talking about the fallacy that anything that's natural is good, right? Oh, it's healthy, it's all natural. Okay, well, this slide can convince you otherwise, because there are many poisons in nature that are typically more poisonous than things that we've made in the lab. And so we have conine here. This is a part of hemlock. So when Socrates drank hemlock tea, it was the conine that killed him. Nicotine, we're well aware of the impacts of nicotine. Atropine is an interesting molecule. It's part of the deadly nightshade plant. And it will dilate your eyes. If you get too much of it, it will kill you. It will cause convulsions, coma, and death. But if you get a small dose, it'll dilate your eyes. So if you've been to the optometrist and they've dilated your eyes, it may have been atropine. They still use atropine eye drops. They use other types of eye drops as well to dilate your eyes. But for some reason in the Renaissance, it was considered a sign of beauty to have dilated eyes. So you have women that would put this atropine in their eyes on purpose to dilate their eyes, which seems crazy. I've been to the eye doctor many times and had my eyes dilated, and it's very hard to see. So I don't know why they would do something like that. But you can see that alkaloids have many, many different effects, and there are many, many different types of alkaloids. There's one that we learned about earlier in the class, histamine. Histamine is an aromatic heterocycle. So let me see if I can get this structure right here. Okay, so I need a double bond there. And then I'm missing a carbon. Yep, they're supposed to 1, 2, 3, 4, 5. There we go. Now I've got it right. So this molecule is known as histamine. The heterocyclic ring is called imidazole, so it's like parole with an extra nitrogen stuck in it. And then you have this ethylamine chain coming off, and that's known as histamine. So histamine is a vasodilator. Its main purpose is to be secreted in the body near wound sites to dilate those blood vessels and get blood flowing to those wounds so the wounds can heal. There are side effects of vasodilation. One is a runny nose. So vasodilators can also increase your mucus secretions. So in allergy seasons, histamine will go into overdrive. And then it can also increase acid secretions in your stomach. So you've probably heard of antihistamines that are designed to decrease the impacts of histamine. And there's two types of antihistamines. You have the ones that are involved in allergy medications that will decrease the mucus secretions. So these are designed to bind to the active site of enzymes that promote histamine's mucus secretion effects. Okay? And then this type of antihistamine, cimetidine or Tagamet, is designed to bind to the active site of enzymes involved in the secretion of the stomach acids that histamine mediates. So you have two different types of antihistamines, one that's anti-ulcer, one that is anti-allergies. Okay, these are very common medications. And then this type of structure where you have an aromatic ring, an ethyl group, and an amine is very, very common in nature. So dopamine, a molecule that probably everybody's heard of, looks like this. We have this benzene ring, these two phenol groups, and this ethylamine chain. So dopamine is a neurotransmitter, and the pathways that dopamine is involved in signaling for regulate our movement as well as our emotions. So if we get Parkinson's disease, that's the degeneration of some of these dopamine signaling pathways. That affects our ability to control movement. You get Parkinson's disease and you start to have tremors. Okay? And then cocaine mediates the emotion or the mood side of dopamine. So when you take cocaine, that elevates your dopamine levels in the brain and causes you to feel that euphoria from the high. The problem with that, of course, is that your brain adjusts and becomes used to those higher levels of dopamine. And when those higher levels are not there, then you crash. And that's why it's addictive, because you crave more and more cocaine, because now, instead of taking it to feel good, you're taking more and more of it to not feel bad. Okay? So don't take cocaine, obviously. All right. And then we have other compounds in nature that are closely related to these, to dopamine, that have effects on mood, as you can see here, and other effects on our physiology. We've talked about adrenaline before. Mescaline, if you've heard of peyote, that's the hallucinogenic component of peyote. Then, of course, we have methamphetamine. That's a synthetic molecule, not a molecule that occurs in nature, but one that is widely synthesized and unfortunately abused in many settings. Okay? So lots and lots of interesting amines. Let's talk about how to make amines. So there are three general categories of ways to synthesize amines, okay? We can perform SN2 reactions with nitrogen-containing nucleophiles, okay? Sometimes those will give us amines directly. Other times we'll have to transform those products into amines. We can obtain amines by performing reductions of other nitrogen-containing functional groups. The amide would be a prime example. There are other functional groups we can reduce that contain nitrogen and turn them and get amines as the products. And then the third method we'll talk about for preparing amines is known as reductive amination. So this is a reduction reaction, so we could put it in category 2, but it's a very, very useful, very, very powerful reaction. So we're going to kind of give it its own category and talk about it. So first off, let's talk about using amines themselves as nucleophiles. We learned that ammonia is a strong nucleophile. We learned that other types of amines can be strong nucleophiles. Sometimes their bulk makes them less nucleophilic, but many times we can use amines as nucleophiles in SN2 reactions. So we can take an amine, react it with an alkyl halide, and that's going to give us an ammonium salt. Okay. So we get an ammonium salt that looks like this. If we have a second equivalent of our amine, that can act as a base to deprotonate our ammonium salt. And that gives us, sorry, not a primary amine. That's going to give us a secondary amine. We've converted a primary amine into a secondary amine. And then we've made a salt as a byproduct. Okay. So this would look like a very straightforward and simple way of constructing amines. We alkylate a primary amine to get a secondary amine. We alkylate a secondary amine to get a tertiary amine. But there's a problem with this. And the problem comes from the fact that our secondary amine is also a nucleophile. Yes, it's not going to be as good of a nucleophile as our primary amine because it's going to be more sterically hindered. But as the concentration of our secondary amine grows in solution, then it's going to start to compete with our primary amine for reaction with our alkyl halide. So we'll get polyalkylation, we'll get mixtures of products. We could probably get a major product, but the minor products would be difficult to separate from the major products. And so this method is not a generally useful method of constructing amines. It is useful in two specific cases. Okay? The first case would be using excess ammonia as our nucleophile. Okay, so we'll take our primary alkyl halide. We're going to react that with ammonia. We're going to use excess ammonia. That's going to give us our primary amine. And then the excess ammonia will deprotonate the ammonium that we get. We showed you that step right here. So we're going to get our propylamine in this case, and then we're going to get this ammonium bromide salt as a byproduct. Okay. If we use excess ammonia, we're always going to have a much higher concentration of ammonia than we do of propylamine. So the ammonia is always going to outcompete the propylamine for the SN2 reaction. So in this case, we'll get a single product. It's not a problem to use excess ammonia because ammonia is a gas. At the end of the reaction, it's just going to bubble out of your reaction mixture when you open it up. Okay? If we tried to use excess of a primary amine in a pathway like this, you would at the end of the reaction have a mixture of secondary amine and unreacted primary amine. those two compounds would be quite difficult to separate from each other. Their polarity would be very similar. They would be hard to separate. So using excess of the amine is really only practical when you're using ammonia. Any questions? All right, and then another case where this is useful is when we are trying to make quaternary ammonium salts. Let's say we have a tertiary amine. So here we've got NN-dimethyl cyclohexylamine. And we're going to react that with bromomethane. We're going to perform our SN2 reaction. We're going to end up with an ammonium salt that is not a nucleophile. There's no more lone pair on the nitrogen. That cannot react as a nucleophile. So if you want to make a primary amine, you can use excess ammonia. If you want to make a quaternary ammonium salt, then you can just alkylate a tertiary amine. Those are the two cases where amines as nucleophiles are useful for generating other amines. Any questions? For the cases when they're not useful, we have some other methods that can be employed to generate amines. And the first one we'll talk about is the Gabriel synthesis. This uses SN2 chemistry, but it uses a nucleophile that's not an amine that will only react once and can be converted into an amine. Did you have a question, Trent?
Yeah. That reaction that you want to talk about, that only work for tertiary amines, or could you just have like a primary amine also going?
It only works for tertiary because if you try to monoalkylate any other type of amine, the product is still a nucleophile. And so that's where you will get mixtures. Okay? So it only works with tertiary amines, or you can use the trick of excess if it's ammonia. So the Gabriel synthesis uses a molecule called phthalimide. Phthalimide is as difficult to spell as it is to say. It's spelled P-H-T-H-A-L-I-M-I-D-E. Phthalimide is relatively acidic. It has a pKa of 10, which means that we can treat phthalimide with hydroxide, usually coming from potassium hydroxide or other hydroxide bases. And that's going to irreversibly deprotonate phthalimide to generate its conjugate base. Okay. Why is phthalimide relatively acidic? It's much more acidic than an amide is. Why is it much more acidic than an amide? Take a look at the conjugate base and tell me what you think. What can we do with this conjugate base? Yes, Grace? It is resonance stabilized. Okay. So we can delocalize that lone pair into a carbonyl. We can do that with any amide. But in this case, we have two carbonyls. So we would have two major contributors where we end up with negative charges on oxygen. Okay. So here's one major contributor of that conjugate base. And then we can draw the other major contributor by using these curved arrows. And as I'm drawing these resonance structures, another thing you'll notice when you look at them is that they are conjugated. These major contributors are conjugated in that the double bond, the carbon-nitrogen double bond, is conjugated to the benzene ring. Okay, so we have resonance, we have conjugation, and so this is a stabilized conjugate base, making phthalimide comparable in its acidity to 1,3-dicarbonyl compounds, such as 1,3-diketones, beta-ketoesters, those types of molecules. So what we can do is we can take the conjugate base of phthalimide. The most common one is the potassium salt, potassium phthalimide. It doesn't have to be, but that's usually the most common one. We can take that and we can react it in an SN2 reaction with a primary alkyl halide. Okay? It has to be a primary alkyl halide. This is a fairly bulky nucleophile, so it will not react with secondary alkyl halides. Only SN2 reactions with primary alkyl halides. Okay? So in that SN2 reaction, we can attach that primary alkyl group to the nitrogen. Okay? Now that we've formed that carbon-nitrogen bond, we need to turn this into an amine. And we do that by hydrolysis, by hydrolyzing the imide functional group. When we have a nitrogen between two carbonyls, that kind of looks like an anhydride. But with a nitrogen, it kind of looks like an amide. It behaves kind of like an amide. And so we hydrolyze it in the same way we would hydrolyze an amide, with hydroxide, water, and heat. And so the mechanism of that imide hydrolysis would just be two consecutive amide hydrolysis reactions, mechanisms of which we learned back in chapter 22. So that's going to give us our primary amine. We're almost out of space here, but I should be able to draw the other byproduct that is obtained. That's too close. I need to move it. We get the dicarboxylate species because we're in basic conditions. These are going to be the carboxylates rather than the carboxylic acids. Okay? Any questions about our Gabriel synthesis? So this may seem like a complicated way to get around the polyalkylation problem, but it's not. It's actually pretty simple because the first step, deprotonation of the phthalimide, is super easy. Then we just have a straightforward SN2 reaction. Then we just add some base, water, and heat, and we get our amine. So even though it's 3 steps, it's 3 fairly simple steps. But it only works with primary alkyl halides, and it only gives us primary amines. Okay? So we can also obtain amines by reducing nitrogen-containing functional groups. And the first one we'll look at is the nitro compound. We learned about this back in chapter 18, where we can reduce nitro compounds to give primary amines. We can use hydrogen and palladium carbon, or we can use iron with HCl, or we can use tin with HCl. Okay? And these can be either aryl or alkyl nitro compounds, but this is more common with aryl nitro compounds because, as we learned in chapter 18, it's very easy to nitrate an aromatic molecule. We cannot attach an amine, we cannot attach NH2 directly to a benzene ring, but we can attach a nitro group, and then if what we really wanted was the amine, we simply reduce it. So this is a very common method of generating aryl amines. Okay? There are other functional groups that we can reduce to make amines, and there's one that's not shown in the book, but it should be, because this is very common, and that is the azide. Azide is N3. Okay? We learned N3 minus as a strong nucleophile back in chapter 7 in SN2 reactions, azide ion. So if we have an azide, we can treat that azide with hydrogen and palladium carbon, or we can use triphenylphosphine, a molecule we encountered in the Wittig reaction, along with water. These two sets of reaction conditions will convert an azide into a primary amine. So this is very useful because it provides an alternative to the Gabriel synthesis. So we could take an alkyl halide, bromoethane is an example in this case. We can react it with sodium azide. That's going to give us our alkyl azide. And then if we reduce that alkyl azide, we're going to convert that into an amine. Okay? Same result as the Gabriel synthesis, primary alkyl halide converted to primary amine over 2 steps in this case. Okay? We've used this in my lab repeatedly as a method of making amines. Okay? So not in the book, but an important method for generating amines. Another functional group that we can reduce is the nitrile. We learned that lithium aluminum hydride reduces nitriles to generate amines, and then we add water. Okay, this also gives us primary amines. So we can make nitriles using SN2 chemistry, using something like sodium cyanide. And then we can reduce the nitrile, lithium aluminum hydride, followed by water. And we see that this is complementary to the azide route or the Gabriel synthesis. Here we're converting our primary alkyl halide into a primary amine, but we're adding a carbon to the chain. So the Gabriel synthesis and the azide synthesis converts the primary alkyl halide to an amine without changing the chain length. When we use a nitrile, it lengthens the chain. Any questions? By 1 carbon. So all these methods we've shown you so far are making primary amines. What do we do if we want secondary or tertiary amines? Well, we can reduce amides. So we can take an amide, and we learned back in chapter 21 that the product of reducing an amide is an amine. Now we can have primary, secondary, or tertiary amides, right? If these are both hydrogen, this is a primary amide. If one's hydrogen and one's an alkyl group, it's a secondary amide. If these are both alkyl groups, it's a tertiary amide. So when we reduce the amide, we obtain the amine that corresponds to the type of amide we started with. A primary amide is going to give us a primary amine. A secondary amide is going to give us a secondary amine. A tertiary amide will afford a tertiary amine. So this method is broadly useful because we can make all types of amines. And we know how to make amides. We learned how to make amides in chapter 22. Another reduction method is, for making amines is known as reductive amination. Reductive amination involves the use of an aldehyde or a ketone. And then we use an amine. We'll use ammonia in our first example. You do need mild acid. The book leaves this out, so please don't leave it out. You'll see why we need mild acid in a moment. We learned in chapter 21 that ammonia, or a primary amine, reacts with an aldehyde or a ketone to give an imine. Okay, so here's the imine that would result. Now the imine is in equilibrium with the iminium ion. The iminium ion is the precursor to the imine. And the iminium ion can be reduced by a special reducing agent called sodium cyanoborohydride. It's very similar to sodium borohydride, but it has a cyano group replacing one of the hydrogens. Okay? This is less reactive than sodium borohydride. There's a negative charge on the cyanoborohydride ion. That negative charge is spread out across the hydrogens and the cyano group. Because the cyano group is a good electron withdrawing group, it takes most of that negative charge, leaving a smaller amount for the hydrogens than what we have in sodium borohydride. So this will not reduce aldehydes or ketones. it will only reduce iminium ions. Iminium ions are more electrophilic than aldehydes or ketones because they have a positive charge. So you can mix sodium cyanoborohydride with an aldehyde or a ketone and an amine. As long as you have mild acid present, you'll get an iminium. The iminium will be reduced. You get your amine. If you use ammonia, you're generating a primary amine in this reaction. If you use a secondary amine, we'll do that over here since we erased. Let's take our ketone. Let's react that with a secondary amine. Or I'm sorry, we'll do a primary amine first, okay? We take our primary amine, mild acid, and our ketone. We're going to generate an imine. This is the imine that we will form. The precursor to that imine is the iminium. The iminium and the imine will be in equilibrium. The iminium is going to get reduced by sodium cyanoborohydride. And what we're going to obtain is a secondary amine. Okay? Now, if we use a secondary amine in a reaction with an aldehyde or a ketone, and we'll just use two of the same group to make it simple on our secondary amine. It wouldn't have to be. We react that with mild acid. We remember from chapter 21 that the product of a secondary amine and a ketone or aldehyde is an enamine, but the precursor to the enamine is the iminium. So we form the iminium. The iminium gets reduced by sodium cyanoborohydride, and the product is a tertiary amine. Okay? So we can use reductive amination to make primary, secondary, or tertiary amines, and we're forming this carbon-carbon bond or carbon-nitrogen bond in the process, the carbon-nitrogen bond linking the amine to the aldehyde or ketone that we started with. Any questions? So that's a very versatile reaction. We'll say a little more about it on Monday, and then continue on into reactions of amines.